Okay, so we're going to continue with our discussion of things nuclear by talking about kind of the nuclear fuel cycle, nuclear industry waste, and accidents. And before I get into this, I just want to mention I'm going to assign the homework 4 today, which we'll do with your final. It's all done, but I need to photograph the questions from the textbook to add it to it, so in case you don't have the textbook. And also, I've put up a PDF in our PowerPoint describing the final paper in the assignments folder on La Lima. I'll talk about it next time, but feel free to look at it now. I'll do the formal assignment on La Lima, which is just going to point to the PDF. The PowerPoint just maybe it's easier to read, and I include the grade sheets in there for the various possible ways you can do it, so you can make a decision about maybe how you want to do the test. But anyway, that'll be due on the day of our final, which is the Thursday of finals week. So today we're going to talk about kind of nuclear activities in the U.S. And I'm focusing on commercial sector here, not the military. And we'll focus on radioactive waste issues and disposal. Then we'll compare that to activities outside the U.S. And then we'll do a little focus of looking at sediment records of fission products in the main testing site in the former Soviet Union, which is now Russia. And then we'll talk about 3 notable civilian accidents. And then you can see next time we're talking about depleted uranium and various things. And then following on after that, there should be a split in here. The final lecture will be on the strontium-90 and yttrium-90 topic. Okay, so when we think about radioactive waste or radioactive waste disposal, we can think of it in a couple of different ways. So within the United States, we distinguish what we call low-level waste and high-level waste. It's just like it sounds. It's sort of what is the activity and what are the isotopes. And so we'll look at both of these issues. And then we're going to spend a little bit of time looking at environmental radioactivity of the Great Lakes region, which is an area of great focus of the commercial nuclear industry in the U.S. Not the only place, but a place where a lot of activity goes on. So a lot of work has been done there looking at the environmental radioactivity. And then we'll kind of, as I say, compare this to Europe and compare it to Russia. So this is the so-called nuclear fuel cycle. And it starts over here by pulling some ore out of the ground, right? Uranium-rich ore, maybe it has 1, 2, 3% uranium, which is a lot, but we want purified uranium. So whereas we may pull, 250 tons of uranium out of the ground, that's going to get converted to uranium hexafluoride gas, like we talked about last time, and concentrated into uranium. And in that process, the 235 enriched material, at whatever enrichment factor it's going to be, goes in this direction, and the rest, which is primarily 238 uranium, goes off somewhere else. And just look at the ratios here. For every 250 tons we pull out of the ground, 220 of it is effectively waste in this process. Okay. Now the military has figured out a way to use this, and we'll talk about that. That'll be their topic next time. I have one slide about it this time, but this stuff here is then it's enriched, and then it needs to be turned into fuel rods, right? So up here it's just pure uranium. It's fabricated into rods. Again, we lose about 1/3 of the material, and that goes into a power plant. And as we talked about last time, because of both irradiation from the neutron flux or doing greater reactions, taking plutonium, neptunium, etc., and fissions, at some point the fuel becomes unstable and it can't be used anymore. And so it gets taken out of use and it goes into storage. And then in an ideal world, this stuff is processed again to take out the waste, the irradiation waste and the fission products, and it goes back into this cycle. And it can be used over and over and over again. And this is what's done in Europe. This is what's done in Russia. This is what's done pretty much everywhere else in the world, including the U.S. military. But in the commercial industry, we don't do this. Okay, we basically stop here and just put all this waste into the ground and go back and pull more out of the ground and do this whole thing over and over again. It's rather inefficient. And the main reason for that is that we don't really have this solution worked out in the U.S. Pretty tenuous situation. So this is just, I showed you how centrifuges work last time, but this is just one more sort of centrifuge picture showing you graphically sort of how at high temperature uranium hexafluoride is a gas, and you spin it and you can separate the 235 from the 236. In reality, you run thousands of these things in a cascade because you get really small incremental enrichments. But for every little bit of 235 enriched material that we make, we're making much more 238 depleted material. And it turns out that sometime in the 60s, the US figured, hey, it needs this depleted uranium for weapons, for munitions. And we'll talk about that next time. And I mean, at least they're using it for something instead of waste, but it creates a lot of other potential hazards. Like I said, we'll talk about them later. So this is the US cycle for the commercial industry, where basically we don't put stuff into the ground. It's sitting at nuclear sites all around the country, unfortunately, most of it, and it doesn't get reprocessed and remade into rods. And so this is one of the reasons why nuclear power has had problems with acceptance in this country, because of the issues associated with storing waste instead of reprocessing them, etc. Okay, so we can distinguish low-level waste and high-level waste. In the US, the way low-level waste is worked out is that the states that generate them are responsible for them themselves. Hawaii doesn't have a site for disposal. We send our stuff to a place in Washington. This is a place that used to be a nuclear facility. There was a lot of accidents in the past. The site is now it's called a nuclear reservation. It's so contaminated that they said all they do is store waste there. So that's where we ship our waste. And this includes stuff like medical waste. If you go and have a radiological procedure or commercial products, and there can be lots of different commercial products that have a reasonably high amount of radioactivity. I remember here on campus at one point, we changed all the exit signs. Now they're powered. In the old days, they had a small amount of radium in there and they would glow. And this was maybe 15 years ago. The university required us to pull all of them out, ship them off as waste. It wasn't just us, it was sort of all over the country. And we don't really do that anymore. If you have a watch that glows in the dark, it's probably also got radium in it. So, and then most of the irradiation material from reactors, so whether small reactors or big reactors, the incidental material, stuff that's around the reactor core, not the fuel, but the incidental stuff that can get mildly radioactive is part of that. Now, we have one federally operated site in New Mexico, and it's a pilot site. It's drilled really deeply down, 2,000 feet or so into a very thick salt formation. Salt domes are really good places to put radioactive material or other waste because they're insulated from groundwater. And or if there's groundwater, it's going to have to dissolve all of that salt to get into it. And they're usually tectonically very stable. So this is a place that federal waste goes to. We don't send it there. As I say, we send it to another site. But there's been talk of putting high-level waste here simply because the high-level waste repository hasn't been sorted out. So high-level waste are spent rods, nuclear fuel rods, often abbreviated as SNF, and nuclear weapons waste, right? And so this is obviously military stuff. And it's the same nuclides, but in slightly different proportions. So in the US, since, maybe about the late 80s, early 90s, there has been discussion about we need a high-level waste repository. Remember, nuclear power sort of came online in the US in the late 60s, early 70s. And, we weren't really thinking waste generation in the early days. And then by the mid-80s, people were like, we're going to put our nuclear fuel rods and stuff. So there are various sites that were looked at, and this place called Yucca Mountain was chosen. It's a few hundred miles from Las Vegas. It's in a geologically very stable terrain. It's part of the Basement Range, which is a part of Western North America that's either sinking or rising. That's the Basement Range, and slightly extending. There was volcanism in this area about 2 million years ago, maybe geothermal activity about 1 million years ago, but it's geologically quite stable. So the idea was, think of complicated tunnel complex underground, be able to service it by rail and store stuff in a stabilized form. This stabilized form involves something called vitrification, which is where you basically dissolve everything in a silica glass and make something that's like a capsule of radioactive material. And then that gets put in canisters that have various kinds of linings that protect it from water infiltrating and gamma radiation coming out, as well as encasing and in direct storage of spent fuel rods. They were envisioned to be, something like this down in some little chambers. The waste would be stable there for at least 1,000 years. And, this place is very arid. There's a lot of rain and it's geologically very stable. And so for many years, everyone was happy with this, and there was all sorts of planning going on. I've given you some links if you want to read it in more detail. There's a lot of work done on the geology. The complex was planned out. This is what it would look like in sort of the rail system, bringing these canisters to deliver them to that vertical emplacement zone. And, there were pictures of what it would look like as Department of Energy, and tunnels are built. The whole project is basically built. And then at the very sort of last minute, politicians got involved in Las Vegas. Oh, we don't want this in our area. We think it might get into the groundwater. Probably very unlikely. There isn't much groundwater. The groundwater is very deep and it's hundreds of miles away. But so basically, even after being built, it's been on hold. And if you go and look, there's not much. Nothing was done during the Trump administration. There was some stuff done near the end of the Obama administration where they were like, okay, we'll go back, and there was some court stuff, and then we'll do some more safety evaluation. And pretty much in 2015 was where most of the activity sort of stopped, where it was determined to be safe, it's determined to be functional, and yet they couldn't get over this impasse of, and what's ironic is that people in the area of Nevada where it was built, they encouraged it originally because of all the jobs and so forth. But then once it's built, it's like, we don't want to use it. So the problem is that this is the waste repository plan for the United States. And in the meantime, the waste is just building up everywhere. So this is a map of nuclear power plants in North America. Some of these, it doesn't distinguish between whether they're active or inactive. Like now all power plants in California are inactive. They're still there. And because there's no waste repository, they're storing waste on site. And I can guarantee you with absolute certainty that the storage at each one of these sites is A, variable. The conditions of storage are not the same at each site, and B, much less good than they would be at Yucca Mountain, which is wherever Nevada is on this map. I think it's like somewhere up in here. But you can see where they're distributed. And there's way more of them around the Great Lakes and in the Northeast and in the South than there are in the West. But, they're around. And all of these sites are storing waste. So this is the location where waste is currently stored. It's actually more sites than when it was on the last slide because there are some auxiliary sites. And sites storing spent nuclear fuel, high-level radioactive waste, and or surplus plutonium destined for geological disposition. This is a place that they want to go. The Carlsbad, New Mexico, the plant is, I don't know which one of these dots, I don't know my New Mexico geography, but it's one of these dots. Very, very small amount of that stuff is going there because it's not really designed for high-level waste. So in the meantime, we've got high-level waste being stored all over the place. And ironically, the argument for not reprocessing fuel in this country and pulling out the waste, because on top of everything else, you generate a lot less waste, but the volume of waste when you reprocess a fuel is much smaller than storing the whole rod. The spent nuclear fuel rod is, something like 1% of the mass. And so the reason that we don't do that in the United States is not, the argument has always been, it's too easy for terrorists to steal that stuff and use it. But if anyone thinks that the situation of having radioactive material all over the country is safer than that, they're kidding, right? So there's an even more controversial thing. So most waste is stored in water, and the water helps to mediate the temperature of the rods and slow down the neutrons that are coming off the rods to sort of keep them from going to do more neutron irradiation. But after a certain point, rods can be stored in what they call dry casking. And this separates rods from each other. It's also supposed to mitigate some of the neutrons, but it's probably not as stable as a way of storing stuff as when you store it in water, but you run out of facilities. And so all of these sites do what's called dry casking, which is a less safe way of storing spent nuclear fuel. And there's really no kind of public discussion of this. People who are in the know this is at those sites, and they're protected at some level, but it's really not a good situation. So that if, for instance, going back to our conversation about power and energy, consumption in this country and around the world, nuclear is a perfectly good source of energy, but I got to control the waste problem. And until that's done, I think it's really untenable in the United States to ramp up the amount of nuclear that we use. And I think that's just the bottom line. This is a graphic. It's from a very old paper from the 90s, so I understand this is bad. I'm going to show you a better infographic in a second. But I want to talk about the details in this paper, which is from the 1990s, which talks about each one of these dots with a name on it are nuclear fuel processing or refining or power generating facilities. So something involved with the nuclear cycle. And these are the Great Lakes. So Canada's up there and the US is around here. And it kind of tells you what these are. This is a better infographic that kind of shows you where facilities are in the United States that, especially around Lake Michigan, Lake Erie, and in between Ontario and Huron, lots of radioactivity produced, used, and cycled in this area. And it straddles the American-Canadian border, so there are even Canadian facilities. These are Canadian facilities up here. And this area, since the 50s has been receiving, or 60s, I guess I would say, is when activity really ramped up, have been seeing enhanced activity. So the point of that study was to look at, well, how much fallout or local exposure are people getting? Now, I'll tell you, it's a very interesting study, and there's a lot of kind of suppositions and back the envelope calculations that go to show it's probably not so bad. But it's kind of like when you gerrymander a political district where to try and isolate and split up a population of people who are going to vote one way and mix them in with a bunch of other people. If you make your area big enough, then the flux of material coming out of these sites doesn't look that big. But really, the hazards associated with the radiological material processing is most closely associated with being close to one of these plants, right? If you're like 50 miles away, it's probably not that big of a deal. But so anyway, as a little bit of background, this is the fallout that comes out of the sky globally in both precipitation and in air. So wet deposition, dry deposition, it's on the same scale. There's something like a factor of 1,000 less that comes out dry. And this is the global background. And you can see here, there's this big spike between 1960 and 1966. This is from the above ground testing that we talked about last time. The nuclear test ban treaty goes into effect in 1964, it cuts off, and we see both these things drop dramatically. And these dots are just different sites in and around the Great Lakes. This mimics, you would see the same pattern pretty much anywhere in the world. Coming down, but initially very quickly, and then after that much less quickly, but still coming down and continuing to come down with some level of complication. And so the kinds of nuclides that are in here are primarily the longer lived ones, helium-3, which is tritium, radiocarbon, strontium-90, cesium-137, and we'll talk about this one on the last lecture. But there's lots of other nuclides too, and I've just mentioned some of them here. These, for instance, are radiation nuclides from that nuclear fuel cascade, and they're relatively long-lived. But we also have fission products. These are all fission products because you can see that their mass is a lot smaller than 238 and 239. And this is just gross reactivity. It's not distinguishing each one of these things. It's measured with gamma radiation. So this is a table showing you for some of the more common nuclides, tritium, strontium-90, and cesium-137, the amount of inputs into the lake, so integrate over the total lake, in terabecquerel, okay? And you can see here that, yeah, it's pretty big, especially for tritium. All of these are in 10 to the 4th, terabecquerels, huge, huge number. I haven't tried to convert that in my head to curies, but it's a huge number. Strontium-90 and cesium-137 are a lot less, but they're still there. They're significant numbers. And yeah, it seems like whatever, if you look at it, seems like Superior has the highest of all these, and these other ones are kind of intermediate. Ontario might be the lowest, whatever. But that's the relative fallout. Now, one thing I want to mention, and we'll come back to this in the last lecture, is that the main way that some of these nuclides get into the food chain and affect humans is by the foods that we eat, and especially milk. If you think about fallout coming out from everywhere, it's landing on farm fields, they're growing, whatever crops that they use to feed cows, hay, or I don't know what cows eat, grass. But in any event, they incorporate that and they incorporate it into their milk. And so this was actually one of the reasons why the nuclear test ban treaty was signed, because we're seeing all these childhood cancers because all these children were drinking cow's milk. Cow's milk had really high concentration. So these are measurements of radionuclide concentrations in milk. Okay, and these are again in the same area, same regions in Canada and the United States, all around the Great Lakes. And so again, we see the big drop off of both the radioactive cesium and the radioactive strontium after the end of the nuclear test ban treaty, and kind of continue a little bit more cleanly than the fallout from the atmosphere. And that was the main justification for doing it. So, at first glance, it looks like, oh yeah, okay, that nuclear fuel stuff isn't that important. So this is a table that shows you the amount of waste, hazardous waste associated with the operation of just 2 generating stations in that region for a year. Okay, and so you can see here that mining, milling, and refining of uranium ore makes 1.6 times 10 to the 5 tons of waste. So right, that's like 160,000. The fuel fabrication process, reactor operation, they don't split this one up, but they split the type of radioactivity in it that's coming off of it up over there. Alpha activity, beta activity in terabecquerels, and Garrett did put, 1 terabecquerel is 27 curies. So this number here, the total, 1.8 times 10 to the 9th is 3.2 times 10 to the 10th curie. A lot of curies. So, and this is basically the reactor waste, the amount that's generated. This is the quantity again in tons, and these are the activities. And so you can see here that the processing of the fuel, it makes a lot of material, but by comparison, it's not as hot as the stuff at the end of the stream. And most of the stuff is stored here on these sites. So this is sort of, I think this might be the final table, but these are assessments of dose and risk over a 50-year period, right? So annualized, but over 50 years for people living in this area. And 3 things are compared. Natural, meaning stuff that's in the soil and the rock and the food. Fallout, in my opinion, these things are very hard to separate because at least, post 1964, before that, you could separate the difference. There was some natural production in the atmosphere that was falling out that was distinguished from the natural in the rocks and water. But in any event, you can see what these values are in millisieverts. So these are hundreds of the sievert per year, 2.6 and 1.9. Fancy math is done to them to convert them into risks. You can read down in the table how it's done. And somehow the fallout risk ends up being a lot smaller than the natural risk. It's like, it's all justifiable, but it's how people get exposed and why they get exposed and what they're getting exposed to. But somehow these numbers, which are basically the same order of magnitude, almost the same, 2.6 and 1.9, turn into 3.4 times 10 to the 5th and 5 times 10 to the 3rd. But the key point of this article is trying to show you is that compare these numbers over 50 years, right? This is a 50-year risk. So the risk associated with the nuclear fuel cycle integrated over that whole region, and it's even lower, right? So they say this is about 1/10 of the fallout risk, and something much less, like 1/1000th of the natural hazard. And this is the thing I'm talking about when I say, it depends on the area that you're including it over. If you take this amount of radioactivity and spread it over a bigger area, if you define the Great Lakes Basin, even though the hazard is probably mostly associated with close to the plants, you'd come up with a different number here. But I think, and I do believe this, that in general, nuclear power is safe and is safely operated in the United States, and that the radioactive risk associated with most plants under normal operations is very small compared to the natural background. Doesn't mean accidents can't happen, and if there aren't spills and unreported leaks and all that kind of stuff, because it happens like in every other industry, especially the oil industry. But it's probably been overblown because of the accidents, which we'll be talking about in a moment. Okay, I just wanted to remind you some of the values. So those values on it, right? These things here, this was like 2.6 and 1.8 millisieverts. Those are thousandths of a sievert. This is the table I showed you last time. I just added the sieverts on here. So this is 0 to 250 millisieverts. It's 2.6 compared to 250 is pretty low on that table. I also just want to point out, I misspoke when I was showing you this above ground test and the contours. I made a conversion on the fly. I said this was 3 sieverts, and I was wrong. It's 30 sieverts, right? Because it's a factor of 100. The 3 sieverts line is all the way out here. And remember, 3 sieverts is really high, right? It's somewhere up here in this range, fatal in 50%. That's the LV. So I just wanted to point that out. Okay, so if we look at nuclear power plants around the world, okay, and this is a slightly old map, it's about a decade old. So some of these have been decommissioned. There's no new nuclear power plant facilities being built in North America. There are some being built in Europe. There are some being built in Asia. Interestingly enough, and one of the main companies that makes reactors, General Electric, is a U.S. company. But until we get our waste issues sorted, we're dealing with old power plants. Some of these power plants are from the 70s, some of them from the 80s. And as anything goes, after several decades, they need to be decommissioned because they're no longer functional. But you can see there's a big concentration in Western Europe, lesser amounts in Eastern Europe and in Western Russia, a large number in Japan, some in China. I think the number here has grown since this map. Some in India. So they're distributed around, not everywhere, but they're in some places. And I don't mean for you to read this or whatever, but this is a 2-slide table of nuclear power plants, generating capacity, and the amount of uranium required in tons around the world. There's this table, and there's another one with the source. If you want to go look at it, it's up to you. But just to point out that across the entire world, 64,615 tons of uranium every year required to operate them. So that's a lot. Right, it's a lot of mining. So we focus in on Europe. You'll see where the power plants are. There's been a lot of discussion, obviously, about, we'll talk about Chernobyl later today, but these other plants in former Soviet Union. This is the largest nuclear power plant in Russia. I've forgotten the name of it, but this is in Zaporizhia. That's the Dnipro River. One of the things you will see is that a lot of these power plants are associated with rivers, right? So this is the, I think this is the Rhone River coming down. They're associated with rivers or coastlines because they need a lot of water. And so France has a lot, Germany has a lot, England has a lot, and there's lesser amounts in other parts of Europe. The main distinction between Europe and the United States is that they do process their waste. So they generate a lot less of it. This is just a storage pond for spent nuclear fuel rods waiting to be reprocessed in the UK. And so the other distinction is that in the US, we mostly use just uranium as our fuel. In Europe, they use mixed fuels, uranium and plutonium. There's some plutonium is obviously built up. This is one of the irradiation nuclides as a fuel rod is being produced or being used, I should say. But you can also run separate reactors called breeder reactors that actually increase the relative amount of plutonium. Some people do that for weapons so that they can extract the plutonium and make bombs. Plutonium, the rods are a little less stable when they have uranium and plutonium in them, but they pound for pound, they generate a lot more power, a lot more heat, which is really what you're trying to do is heat water to run steam to make a turbine. And waste for weapons productions are minimal because there isn't much weapons production in Europe. So here's just a list of some other countries. And this list is always kind of changing. We're at India, Israel, North Korea, Iran, and Pakistan, and Russia on here. Some of these are more kind of countries are more open with what they have or don't have. Some of these are clandestine programs. Countries have both civilian power and weapons. Like in the US, is a completely stovepipe. They're two separate things. The infrastructure is different. In most of these other countries, there's a lot more crosstalk between what is considered commercial and what is considered weapons. And so, this is just a little bit of history, but some of this goes back quite a long ways. Like Israel developed its first nuclear test facility in the 50s, right? I mean, they never acknowledged that they have a bomb, but please, they obviously have the capability. We know a lot about what happened with North Korea. We know a lot about what happened with Pakistan. Pakistan actually sold their technology to a bunch of other countries, including North Korea. And that's what brought down Gaddafi in the end, is that we caught them selling Libya technology. And so, but this was a homegrown effort, right? They developed it themselves. In Pakistan and India are like, enemies of each other. And India also has a technology. And so it's complicated. But I just want to spend a little bit of time talking about Russia because it's so different than the United States in some ways. So Russia / former Soviet Union. In the days when it was the Soviet Union, the countries that are sort of Russia plus all these neighboring countries like Kazakhstan and Ukraine and Belarus and all those things around here that were part of it, they basically operated under one centralized government. So this is just some of the power plants. And I want to talk specifically about the area in this box, especially up here near their testing facility, which is called MIAC. So they actually had two related sites where they did most of their weapons testing. Something called Tomsk, which is in a place called Seversk, and MIAC. MIAC is now inactive, but MIAC is considered the most contaminated place on the planet. Really gnarly because massive spills back in the 50s and 60s and 70s, which weren't, in the days of the Cold War, we didn't really know about this stuff. It's come out after the fact. Massive leaks into the environment that have just contaminated wide swaths of area, made them so radioactive that people can't live there anymore. So they were doing above ground testing of both these things as well as nuclear fabrication. This site, it's kind of like the US. We still have an active test site too. We don't really do below ground tests anymore. It's in Nevada. This is our quote unquote active site. This is the inactive site. These lines are rivers. So we're going to look at some sediment cores in rivers draining off of MIAC to kind of look at the redistribution of radionuclides. So the irony about nuclear waste in the former Soviet Union is they don't have nearly as big of a waste problem as we have in the US. That's because all along they were just spilling it out into the environment. They were just not worrying about it. So for instance, there's as much as 1.7 billion curies that was poured into rivers and lakes, most of it getting into one particular lake near MIAC, which has left widespread areas of the Russian countryside. This is kind of considered Western Siberia, very, very contaminated. And basically, you can't even visit them. I've given you a link there if you want to check it out more. And this is just a picture of two signs. I had a Russian student in this class a few years ago. This sign says, this is a nature reserve. And this sign says, be careful, this is very radioactive. And in fact, this lake is believed to hold something like 1.2 times 10 to the 8th, or 120 million curies of waste. And there was a drought in the 60s that brought the level of the lake down, and a lot of sedimentation and lake bed sediments were exposed and circulated by winds, and this caused radioactive wind to be blown, many tens of kilometers, about 75 kilometers downwind. It was being detected, this was a region that was an agricultural region. People were farmed there, and so this is why people call it the most polluted place on the earth. It's basically unlivable. Okay, so this is MIAC, that inactive site where the big spill happened, and these things called OB 95-11, 13, whatever. This is the OB River. And it's got various tributaries. It drains up here into the Arctic Ocean, and these are sediment cores that were drilled into it to kind of look at the redistribution. I'm not going to give you data from all of them, but you can see there's some proximal sites and some sort of medial sites, some distal sites. And the idea is, well, how is radioactive material migrating? And you can see here, this is 5 degrees of latitude. A degree of latitude is 110 kilometers. So when we're talking about 15 degrees, we're talking about, I don't know, whatever, 15 times 110 is 1,700 or so kilometers. So long distance. So when we look there, And before we look at the course, I just want to remind you of one other thing. So when we did the above ground nuclear testing, and this is just the USA and the former Soviet Union, which contribute the vast majority to the global fallout. Two of the things that fall out are cesium-137, as we've talked about, strontium-90. Now, the difference between those is cesium behaves very similarly to potassium, which we've talked about before, sticks onto clays and then doesn't migrate very well. And so what we find in a lot of different settings that haven't been disturbed, haven't been bioturbated, haven't been re-eroded, is a spike in cesium-137 that represents the sort of initial production and the peak of production, and it falls off at the tail of the nuclear test entry. People look all around at all sorts of things. They look in sediments in artificial lakes, they look at sediments in real lakes, they look at soils, and they dig down until they find the horizon with this peak, and they say, oh, that peak represents 1964 in stratigraphy. Now, in places that have had disruption, you don't find this peak. So one thing that we're going to look at in the study is they compare the cesium-137 data to plutonium data, find the peak, identify where 1964 is, and look at, does the plutonium follow the track of above ground testing, which was happening in this area, and tail off, or does it look like it's been redistributed up or down section? Okay, so this is a bunch of cores. Each one of them has depths. You have to go back to the map to figure out where they are. But I've highlighted two kinds of profiles. There are profiles that look plus minus like the cesium profile, like this one. Yeah, it's pretty low, and then there was a point where it was higher, and then it goes back down to low. Same thing with this one. This is a little bit messier. This is over 20 centimeters. It's probably been spread out some compared to the cesium. This one here again is pretty good, but then you look at these. This thing here has obviously had a lot of migration of plutonium up section. That either means redistribution in the sediment or is being distributed in the waters and being added as new sedimentary material as the cores accumulate. Here's one, doesn't show nearly as much variation, but it's elevated everywhere, right? Like you can look here down here where these are all in concentration units. This is, this is in 10 to the 7th. This one here is in 10 to the 8th. So the whole concentration of this whole core is higher than the cutoff's about right here, I think. This one here, the data is kind of sparse. So we sort of see two things. We see some where the concentrations are highest, roughly around the time of the weapons testing, and some where it's higher, which suggests some kind of plutonium migration. So the way this was sorted out was looking at the colloidal fraction in the waters of the river, separating out, filtering. These are 10 micron scale bars, so these are small particles. This is a heat map, showing you the uranium-238 oxide and the plutonium-239 oxide concentrations being very, very elevated. This is using something called nanosims. We have a nanosims in our basement. They can be used for all sorts of different things, but you're focusing a really small beam and knocking out elements and then measuring their spectrum and getting their concentration. And so this was sort of proof that very fine particles in the aqueous phase component of the riverine system are carrying high levels of activity away from the site downriver. These particles, I can't remember, they were I think I say on here somewhere, they were collected pretty far away from this Lake Karachai, the really polluted lake near Maya. Colloids 3.2 kilometers from the source. So it gives you some idea of the kinds of migration you can have. Another thing that you can do with the irradiation nuclides, the things that are produced during the nuclear fuel cycle. I've just reminded you, you can look at slide 47 of last time where we had the nuclear cascade, uranium-235, uranium-238, and all the various isotopes. Each of these lines is a different element. This is a line for plutonium, this is a line for americium, there's californium, neptunium is down here. It turns out that how much of each one of these things you run is kind of characteristic of the conditions of the nuclear program that it's doing. And whether it was by design or not, you can fingerprint radioactive material that comes from different places based on the ratios of some of these things. So radiation nuclides, 240 and 239 plutonium, neptunium-237 and plutonium-239, plutonium-240, and fissionogenic product, cesium-137. There's way more sophistication to this than that, but I just wanted to sort of show you that you can, for instance, distinguish using these isotopes the global fallout that's still happening from the above ground testing, what's in the Mayak region, what's in the Semipolynsk region, what came from Chernobyl, right? It's like right after Chernobyl happened, and we'll talk about that next. We knew it was different because it was isotopically distinguished in at least 2 of these 3 ratios. Americium can also be used for this. This is how we know when North Korea did its very first nuclear test. You fly over the country at high elevation planes, you take air filter them, send them to the Los Alamos lab, and they measure these isotopes on really small quantities. And so this is the process of what's called isotope fingerprinting. And there's another plot that plots 2 things against the other, 2 isotopes of plutonium and an isotope of neptunium and plutonium. And what we can see is, yep, here's that Mayak, that really contaminated site. This is the global fallout. They have distinguishing values. And as you can imagine, if you're somewhere not right at Mayak, but proximal to it, so that you might get a little bit of fallout, then you should be in a mixing line between this and this. Now, a lot of these isotopic compositions measured in and around former Soviet Union do fall on mixing lines, but there's 2 populations that are different. There's this population here, which has a higher amount of neptunium than the global fallout, which implies another source, right? And the source, these are sampled after 1986. There's also a high plutonium-240. Chernobyl has a very high plutonium, but it has a very low neptunium. So this just goes to show that we don't know the sources of all the materials. There are multiple different things out there, but in any event, this is sort of how nuclear forensics is done. All right, so now for the rest of the time, I'm going to switch gears and talk about nuclear industry accidents. So the 3 accidents I want to highlight, because each one had a major impact on the trajectory of nuclear power. This one in this country, Chernobyl globally, and then Fukushima Daiichi most recently. Unfortunately, because that was sort of a state-of-the-art reactor. So this is the 3 Mile Island power plant. It's on an island in a river. And basically what happened is there was one of the reactors. Many of these power plants have multiple reactors, right? So reactor 2 was destroyed because the reactor core became uncovered with water. Water's in there to help mediate the temperature and control the rate of the reaction so it doesn't go supercritical. So about 1/3 of the fuel melted. And there were no injuries. There have been no documented adverse health effects. There was a small amount of radioactive steam that was released, but it was pretty well controlled. So in fact, I would argue that this was a demonstration of the safety protocols actually working. It's, the hindsight was that they didn't have adequate instrumentation, and the operators were not well enough trained to prevent the things from happening in the first place. But other than that, and the fact that the public freaked out when this happened, this was, I think, 1979. I've forgotten the year. Yeah, 79. That it really put a damper on nuclear power in the U.S. Now, if we look at Chernobyl, this is a completely different thing. So this happened later, but it happened with older equipment. So in the former Soviet Union, they were pretty early in on nuclear power. They built a lot of power plants using sort of 1st generation technology, which didn't have nearly the same amount of safety protocols. And in essence, this is an assessment from someone else, an independent World Nuclear Org, that it was basically personnel error coupled with very bad design. So they saw something was happening, they weren't able to shut off, and it was like a mega version of what happened at 3 Mile Island. Much larger amount of fuel melted, the core went critical, it exploded, it put a bunch of stuff out into the atmosphere. And maybe there wasn't as much safety culture and isolation and all this kind of stuff. I think some of that stuff is debatable. We know that 30 people died from this, so it was a much worse accident. 2 people died at the plant right away on the night of the accident, and then 28 more died within a few weeks from the acute radiation poisoning. So we know that means something like the 3 sieverts of activity. So when we look at the long-term impacts, is a little bit more complicated. that there do appear to be increased thyroid cancers in the region, but a lot of people were pulled out of the region. And you may know or realize that Chernobyl is actually in northeastern Ukraine. Back in the day when this happens, it was all Soviet Union, but that area has had an exclusion zone around it until the Russian invasion last year, when the Russians reoccupied the site and started digging in the soil and doing what they do with the earth movers and stuff, which is also sort of a secondary concern. So what's weird about this is this was like the height of the Cold War. So the accident happened, and Russians and Ukrainians, they didn't say anything about it. It was only after a radioactive cloud spread far enough to the west. Back in those days, this was all still part of the Iron Curtain, right? These were independent countries, but they were under Soviet control. So you had to go over to the next country. Germany's over here, Scandinavia is up over here, Austria is down over here. They started like noticing a radioactive cloud coming over, like, oh, what's going on? It didn't take very long to figure out that they were releasing super large quantities of radioactive material for like 10 days, unabated into the air. And so, of the amount of radioactivity, two radionuclides are the most concerning, the iodine-131 and the cesium-137. This one's kind of short-lived. Iodine attacks your thyroid. This is why they give you iodine tablets to take, so that you flood your thyroid with not radioactive iodine in hopes that you won't absorb too much of it. Long-lived cesium-137. There's also a lot of radioactive xenon gas, and estimates have been made that something like 5% of the 192 tons of radioactive material there was released in the accident. It's a really, really big amount. Released by dust and wind, and it spread around Europe. The winds changed at certain times. So here's where Chernobyl is. This is the quote-unquote border between Russia and Ukraine. It's certainly amorphous now. So this is where Chernobyl sits. It's really, really up there in the extreme northeast. This is an activity map showing you activities in kilobecquerel, so thousands of counts per second per meter squared. You can see really hot down to sort of not as hot all around the nuclear power plant, with some of this distribution being associated with the winds. And this is specifically for strontium-90. So now we'll talk about Fukushima Daiichi. This was a reactor that's built on the coastline, considered modern. In Japan, the nuclear power is privatized. So this was operated by TEPCO, which is one of the largest utilities. They're the company that provides power to Tokyo as well as other surrounding regions. And as is common also in the US, power plants are oftentimes put by the coast, so you see water that's cooling. And so you can see this is put right on the coast, like a series of breakwater and stuff. But what happened is there was this huge mega earthquake. The earthquake caused a tsunami. The tsunami came ashore. They lost power. They couldn't control. At first, it was just one of the buildings. These are reactor buildings here. Then it was multiple of the buildings. They didn't have an independent means of power to keep the water pumping. They were using the power of their own power generation to pump water to keep the reactors cool. In hindsight, that's a really stupid idea, because when your power plant goes offline, you can't keep your fuel cool. You need to have an independent method of generating electricity to keep your power cool. The difference between this and 3 Mile Island was so dramatic. Excuse me, this and Chernobyl, because this happened live on TV, right? It happened, we knew it happened. You could watch it. This is on the BBC, this is from CNN, and the TEPCO, the operator, was trying to kind of keep people out and trying to limit the amount of information until they at least knew what was going on. There was about 24 hours there of kind of confusion, but this was a protracted accident. So there was a series of spills and a series of kind of worsening effects that spread from one building to the other. It ended up being pretty dramatic, and it caused Japan to also decide that it wants to cut back on nuclear power, as well as some countries in Europe. Again, because of sort of however you want to think about it, in hindsight, safety flaws in the design, and at a time when we need to have sort of non-carbonaceous fuel sources, it's kind of unfortunate. So basically, they lost the power after the quake. 3 of the reactors experienced a full meltdown. They had no water. They were not able to cool their rods. The rods heat up and they melt and go critical. And there were primarily explosions of steam here with really radioactive material in them. There's also generation of hydrogen from a small amount of water that's present. And so there were some hydrogen explosions, and there were large amounts of radioactive material put into the air and into the ocean. This was sort of the first time we had one of these big accidents where we were directly putting radioactive material straight into the ocean in a place where, marine resources is a big part of the food cycle, right? In many countries, it wouldn't matter as much, but there was and continued to be questions about, well, how much is this stuff migrated to other areas? Is it in the seaweed? Is it in the fish, etc.? The full extent of the damage a year after the fact was still not known. There's been a lot of scientific studies that have better documented that most of the issues were probably restricted to the vicinity of the plant. In terms of the ocean, concentrations attenuate very, very quickly. There was some deposition over land. And the size of this event, which we can document much better than Chernobyl, was comparable to Chernobyl. They weren't exactly the same, but they were comparable. So this is just a timeline. This is from some German scientists of, so this is basically one day, another day, etc. Various kinds of explosions, and then sort of working out, this was from reactor block 2, reactor block 3, or whatever. And so these went on for multiple days, very large explosions happening in sequence. And at some point, they basically decided, we don't have power, we can't get our fuel rods shut off, so they flooded the whole facility with seawater. And that stopped the explosions, but it caused even more problems potentially for contamination, because now you've got large quantities of contaminated seawater. So these are measurements, again, in microsieverts per hour. So a microsievert is 1,000th of a millisievert. But you can see these numbers go up, pretty high, 20,000, for instance. And these are just different locations, different towns in and around the area. It was evacuated, and a lot of people didn't understand why they were having to be evacuated. It was right after an earthquake. It was already sort of turmoil. But you can see that depending on where you are, I don't know the geography, I don't know which one of these places is close or far, but some places had kind of a continuous fallout that lasted many, many days. Other places had more punctuated fallout, probably more associated with the specific explosion. Some places, had punctuated things that lasted, many days. And so this, gives a concern about when is it safe to repopulate the area, how much radioactivity is in the soil, etc. And this is just looking at the contamination coming out of this contaminated seawater that was put in to cool the rods, after about a week. And you can see that in terms of the short-lived radioactive iodine and the longer-lived radioactive cesium, much elevated reactivities on kilobecquerels was being measured, more than a month after. And they stopped making measurements, or maybe they're continuing making measurements if that's when this article was written. And so, a long-term radioactive source. So, after the fact, basically, the plant was put into cold shutdown, it was decommissioned, and the TEPCO, the operator, basically decided they were going to cut back heavily on nuclear fuel in their country, which, totally understandable, but at the same time, Japan started to increase the amount of carbonaceous fuels that started burning, contributing more to global warming. So these things, they're all kind of interrelated, and it's unfortunate that the plant wasn't designed a little bit differently. So here's a little bit of information more about the doses that were released into the environment. This one was studied much better than Chernobyl because it happened in real time. It happened in a country with an open and free communications between scientists and academics and the government. And so scientists from other countries were coming in, obviously Japanese scientists as well. And so really high concentrations of activity in sediments. These are in becquerels per kilogram of material in the fish, in the algae, I mean, up to 100 million becquerel per kilogram. Think about organisms that eat algae, for instance, whales, which are part of the diet in Japan. These are in Japan was considered legal. 500 becquerel per kilogram of cesium-137 and 2,000 of iodine-139. So obviously, these numbers are potentially, at least in the region, much, much higher, which meant that they started putting in controls on catches and stuff. But, you know, and this is a quote from this particular article, which you can get there, you know, the doses will decrease quickly with time and distance, which is always true with reactive decay, especially something like iodine-131 with a short half-life. Cesium-137, not so much. It's going to take a lot more time for decay, but you do have dilution with distance because you have mixing in with natural materials that aren't radioactive. So this is kind of a comparison of those three disasters. So this is kind of international scale, INES, which is kind of like a Richter scale. It's a magnitude, each number up is a factor of 10 worse. In trying to sort of relate these three biggest accidents together, Three Mile Island has been given a 5. Chernobyl and Fukushima have been rated a 7, which means they're approximately 100 times worse. The number of deaths, 0, 30, and 0, although that 30 has an asterisk with it because there were 3 workers that died after the fact in physical accidents, not because of radiation, but you know, other mishaps that happened in the days after the accident. So some people would include them, other people don't include them. And you know, one of the questions we have is, were these two things equivalent in the severity? Chernobyl, we know so little about because it happened behind the Iron Curtain. So what we know is that in terms of iodine-131, there was probably about 1/7 as much released at Fukushima as at Chernobyl. So in that sense, Chernobyl was probably worse. But much of the Fukushima reactivity went into the sea, which we weren't able to document very well. Right? It's easier to document fallout over land because it's preserved in the land surface. You can actually sample asphalt, surface soils, etc. Whereas a lot of the reactivity goes in the sea, it disperses and dissolves. So we're not sure about that number, about the 1/7 number. And it's really too early to estimate the Fukushima health impact in the long term. This is just another infographic from another source, kind of showing you a comparison of the three in terms of the orange circle is the area that was affected, and you know, just some kind of basic stuff about each one of the you know, the evacuation zone, etc. The number of people in the population that were affected, and so I think you can see that, you know, on the basis of this, in terms of where radioactive material was found in surface soil, Chernobyl was bigger. Whether it's a factor of 10 bigger, so it should actually be an 8 instead of a 7 or whatever, I don't really know, but probably it was a worse accident. This is a map showing you the fallout of cesium-137 as measured in surface soils from Chernobyl. What happened with the Chernobyl accident is initially the winds were blowing this way, and then they switched, and then the winds were blowing stuff back into Russia. So if in fact, if the winds hadn't been blowing this way at all, so, you know, to be able to be picked up, you know, in these Western countries, we may not have even really known about the accident. It took the Russians many years to come clean about what actually happened. This is a fallout map, the equivalent fallout map for Fukushima. But again, the significant part of it being over the ocean where there's no way to really track the cesium-137. I mean, there are boats out there pretty much right away soon thereafter, but it's not the same. It just disperses into the ocean and so forth. So I think that this slide here is just a comparison of the two, right? So this is a map of Japan, and this is this same Fukushima thing. That's this. And then this has been superimposed on it as if it happened in Japan, just to compare the sizes. It's just a Google Earth thing. And you can see that the Fukushima fallout really was smaller than the net effect of Chernobyl, which spread over a much wider region. So probably either Chernobyl was underestimated in that INES scale, or scale needs a little bit more thinking, but there's so few accidents to base it on. This, you know, semi-quantitative, I would say. So that's the last slide. And do you guys have any questions about this stuff? Okay. Well, we're getting in a little early today.